Hi, I'm from Team Antonio. We're going to discuss about advanced surface construction techniques. I'm Livia and my teammates are Priyanka and Shweta. So these are my team members' contributions. The topics we're going to discuss under advanced surface construction techniques are swung surfaces, skin revisited surfaces, swept surfaces, cordon surfaces, Coons surfaces, and some design examples. Swung surfaces. So swung surface is a generalization of surface revolution. Surface revolution is like the trending kind of surfaces that are used in the field of engineering. So in the construction of a surface of revolution, the profile curve performs a complete rotation about the axis of revolution and is never scaled. By the term never scaled, I mean that the shape of the profile curve is never changed in the course of rotation. So here the profile curve is defined as P of U, and the trajectory curve is defined as T of U. As you can see, the profile curve is defined in the xz plane and the trajectory curve is defined in the xy plane. Profile curve is given by this formula and the trajectory curve is given this formula. We can define the swung surface by the following formula: Su comma V is equal to alpha into P of x of u into T of x of u, comma alpha into P of x of u into T of y of v, comma Pz of u, where alpha is an arbitrary constant. Geometrically, S of u, v is obtained by swinging P of u about the z-axis and simultaneously scaling it according to the trajectory curve. S of u, v is equal to summation I to 0 n summation j to 0 m r of I p j q u of v k of I j, where k of ij is equal to alpha into pi of x into tj of x, comma alpha into pi of x into tj of y, comma pi comma z, where wij is given by w1 into wj, where it is the weights. The u and v naught vectors for s, u, v are those defining profile curve and the trajectory curve. From the previous example, we seen the curves, this one. So from this, we're gonna add alpha is equal to 0.2. As a result, we get this control points. Whereas the surface of this figure was obtained by applying weights for W1 equal to W4 equal to 5, and for trajectory curves, taking W1, W4, W6 and W9 as 5. As you know, the superscripts P and T refer to profile and trajectory curves. Here is one of the design examples for the swung surfaces. This is like a flower vase which is cut as a cross section. As you can see, these are all the control points using which we designed a surface. This is the swung surface design example. Next, coming to skin surfaces. A skin surface is a surface that contains a given set of curves C1, C2, so on, Cn. As you can see in the picture, from C0 to C4, there is a various slight differences between all the curves. It is a straight line and all the sharps and all the curves can be seen in these curves. Skinning is simply a newer term for lofting, which dates back many decades before computers. Based on B-spline, skinning is defined as follows. So you can see the example. The K ranges from 0 to capital K. This can be a rational or non-rational section curves. It is assumed that all Ck of W defined on the same knot vector U have a common degree P. So for V direction, a degree Q is chosen and the parameters Vk and knot vector V are computed. These are then used to do n+1 curve interpolations across the control point of the section curve. It yields a Qi of j, which is assumed to be the jth control point of the interpolating curve through Pi0 to Pik. The section curves are defined on the following knot vectors. So from C0 of u, where the parameters are 0, 0, 1, 1, p equal to 1, we go on till C4, where we take the degree p to be 3, and these are the parameters. So after the degree raising and knot refinement, the common knot vector is given as the below. As you can see, the common knot vector is a pretty large number. So this helps us see how the skin surfaces are really big and difficult to do. The control points seen in this figure is taken to be 22. As you can see, the number increases. The control point net and the skin surface are given in the example here. So the control points are taken here, which is converted to the skin surface. Although simple to formulate, it is quite difficult to implement a robust and usable skinning capability. And interactively designing the skin surfaces is a tedious and iterative process. Surface shape is difficult to control. It depends on the number, shape, and positioning of section curves as well as the method of V-direction interpolation. Skin surfaces can exhibit unwanted self-intersections. However, skinning is a powerful and widely used surface design technique. It is mostly used for designing aircrafts, automobiles, and ships. V-direction interpolation. Assume for a moment that all section curves are non-rational. The problems with other curves are dealt in the next slides. So three items must be determined here. It is the degree q, the parameter vk, and the knot v equal to vi. The only restriction here is that the q should always be less than or equal to capital K, and the degree q is arbitrary. The VK is calculated by the following averaging technique. So here is the averaging technique that we're going to use. Here DI means that the total chord length where it ranges from PI naught to PIK, and then the knots VI are then computed using this averaging technique. Another common method is to use spine curve. That is, using this formula we can calculate the path. Cs of V can be an arbitrary rational or non-rational, planar or non-planar curves. The designer uses the spine curve to position and orient the section curves in space. So here is an example of the spine curve. As you can see, there's cross-sectional curves. These are called as 5 planar section curves. So this is one of the possible positioning of the spine curve. The section curves are positioned at the spine parameters Vk and Uk as shown in the slide. Each section curve is oriented so that its plane is perpendicular to tangent vector of the spine curve at the intersection of the spine curve and section's plane. The spine curve can also aid in V-direction interpolation. V-direction interpolation as we see in the previous slides. So let Vk, k ranging from 0 to k, be the V values of the point on CSV where the section curves are positioned. Now taking Pk dk where k ranges from 0 to k, then for each I and k, we'll compute a derivative vector dik, and for each of this I, it yields 2 into k plus 1 interpolation constraints, that is pi0 to pik and di0 to dik. The dik are computed by letting dk equal to pk minus 1, where k is equal to 1 to k. So that is how it is 2 into k plus 1. So then for k equal to 1 to k minus 1, these are calculated, and at the end di0 is calculated using this formula. As you can see in the picture, this dik is always parallel to dk, but its magnitude is adjusted to reflect relative distances. So assuming m is equal to 2k plus 1, we can set m plus 1 linear equations for each fixed I, that is using these two formulas. The knot vector v must contain m plus q plus 2 knots at the end. So the following figure shows the control points of the skin surface defined by the data shown earlier. We use cubic interpolation with specified derivatives. So using specified derivatives, these are the control points, and using the control points, we create a skin surface. In the next example, we see the control points without the specified derivatives and how we derive the skin surface without the specified derivatives. So the skin surface revisited will be continued by my friend.
Hello everyone, let's see what skin surface revisited is. A surface S is a skinning surface for the sequence of sets C0, C1, Ck if it satisfies two conditions. That is, S interpolates the set, and the other is there is a continuous function f of S201 such that Ci is equal to f inverse of Ti. And the real number 0 equal to T0 less than T1, so on, less than Tk equal to 1. The second condition focuses that we have coplanar and cross-sectional curves without any intersections. So let's see what is skinning in practice. Skinning is the more recent term for lofting. The set Ci consists of one or more curves in which they are sometimes called skinning curves. Different skin surfaces are made using different constructions. So a certain order of curves gives you a certain skin surface, and the change in the order yields a different skin surface. Thus, the order is important. Next, let's see what are the problems caused for lofting problems. So, surface skinning is also known as lofting as we have seen before. So, it is a process of passing a surface through the so-called cross-sectional curves. What are the causes of lofting problems? One is parameterization inconsistencies, position inconsistencies, continuity inconsistencies, weight problems. So, in parameterization inconsistencies, the parameters must flow the same way along each section curve. As we have seen that the skin surface has section curves, so we require that every section curve's parameters must flow the same way. Next is positioning inconsistencies. Here, section curves must be placed with care or wiggles, or even self-intersections may occur. So we have to see that the section curves must be placed with utmost care such that there are no intersections. Next is continuity inconsistencies. Rational curves must be parametric continuous in homogeneous space, not just in Euclidean space. So when we build up the rational curve, they should all be parametric continuous in the homogeneous space. Next is weight problems. Large weight changes may cause negative weights during interpolation, and weight scaling may produce nonsensical surfaces. So we know that even though all the weights are positive, the large weight changes may cause negative weights during interpolation. Next, let's see what is skinning to approximate cross-sectional curves. So we have a method here called B-spline surface approximation method, and it consists of four phases, that is branching problem handling, counter alignment, and construction of closed B-spline contour curves on a common knot vector, surface scanning of the B-spline curve. So the first one, branching problem handling. Decompose each multiple branching problem into a set of single branching problems such that we have to decompose the M and M to N branching problems to one single branching problem such that we have M plus N counters for each M plus N elements. So the counter alignment. The second step is to determine a good baseline for each single branching region and align them for the baseline. So it is what we have got in the before step, the single branching problems. We have to determine a good baseline for all these and align them to a perfect single baseline. The third step is construction of closed B-spline contour curves on a common knot network. So the B-spline curves are required to make compatible for surface skinning. So here, all the B-spline curves that we have got are required to make compatible for the surface skinning. The surface skinning of the B-spline curve is the last step. By skinning the intermediate closed B-spline curves constructed on the common knot network, we generate a bicubic closed B-spline surface. So this is the method of how the B-spline surface approximation is done. So next, let's see what are the problems existing. There exist several potential hazards which cannot have a satisfactory practical solution. They arise as a result of the fact that surface construction is being done in homogeneous space and the corresponding three-dimensional and four-dimensional space can be radically different. That is, when we construct the surface in homogeneous space, there might be chances that in that three-dimensional and four-dimensional space, the construction can be radically different. More specific problems that can arise are the v-directional surface parameterization may be rather poor. Interpolation can produce a negative or zero WIK even though all the section weights are positive. This can cause problems such as system crash downstream in a system. So here Even though all the section weights are positive, as we have seen, a big weight change can cause a negative or zero weight during the interpolation. So this is a more specific problem that arises. The next one is, the surface may be not as smooth as the suction curve indicates. So this is the example for skin surface revisit. So here we can see that we have 6 circular curves arranged in the form of a pipe of arranged in the form of bent 90 degrees. That would seem like a pipe. So here we can see, like, if you have moved the arrangement of the curves like in different direction or in different angle, then the pipe structure can change. So this is it. We can continue further with the other topic.
Swept surfaces. Swept surfaces are generated by moving a section curve along a trajectory curve. Let us denote the trajectory curve as T of V and the section curve as C of U. Then a general swept surface is given by T of V plus M of V into C of U. So here from the figure we can see the trajectory curve and the section curve. And this M of V can be a 3 by 3 matrix incorporating rotation and non-uniform scaling as a function of V. The transformation must include translation and or rotation and may also include scaling and shearing. Generally, sweep representations are used to construct 3D objects from 2D shapes that have some kind of symmetry. Translation sweep. We can construct a prism using a translation sweep. Let us define a shape as a polygon vertex table as shown in figure A. Define a sweep path as a sequence of translation vectors figure B. Translate the shape, continue building a vertex table figure as shown in figure C. Then we can define a surface table figure D. Example of swept surfaces. The example of swept surface can be a swept tube. With swept surfaces, a tube does not have to be linear like a cylinder or circular like a torus. One can use a circle as a profile curve and another curve as a trajectory curve. The following shows a circle in the xz plane as a trajectory and an ellipse of degree 3 naught in the xy plane as the trajectory. From the wireframe figure shown, you will see that the tube is narrower than the two ends. This is simply because the profile circle moves in parallel with each other and as a result would stack together near the place where the trajectory curve does not change shape fast enough. Moving to rotational sweep. In the rotational sweep, we can take an example like we can define a shape as a polygon vertex table as shown in A. Then define a sweep path as a sequence of rotations. Then rotate the shape, continue building a vertex table as shown in figure B. Then we can define a surface table as shown in figure C. Swept surface construction. There are mainly 3 steps in creation of a swept surface. And the first step is refinement of selection. And the second step is extraction of trajectory. Third step is refinement of trajectory and extraction of profile curves. In refinement of selection, the shape of the swept surface region is very important in subsequent analysis and editing. To ensure that we meet these criteria, we require to consider the smoothness of both the curve and the normal of the original mesh along the curve. In extraction of trajectory, the trajectory extraction is the pivotal step for creation of the representation. To create a meaningful swept surface, traditional skeleton is always the best idea. In refinement of trajectory and extraction of profile curves, the profile curves are extracted by the intersection of the cross-sectional planes and the mesh. Swept surface with no trajectory control interpolation. This is an example algorithm for creating a swept surface with no trajectory control interpolation. We can take input of control points and trajectory and BV and SV as input functions, and Q and K needs to be minimum. Then by performing the transformation and positioning, we can generate an output of a swept surface with no trajectory control interpolation. Similarly as seen as above, but this is different from the above figure, like this is a swept surface with trajectory control interpolation. We take input as trajectory control point, then BVSV as input function, and K needs to minimum. By performing transformations and positioning, we get a output of a swept surface with trajectory control interpolation. Here the two figures varies by one is swept surface with no scaling and another one is swept surface with scaled sectional curves. Both the figures show sweeping examples where the section curve passes through the origin. The first figure used no scaling while the other one used a piecewise linear B-spline scaling function defined by control points. Swept surfaces with no trajectory control and swept surfaces with trajectory control. The previous two examples we discussed were involved of a planar trajectory curve, and these examples show a three-dimensional twisted trajectory. The trajectory was not maintained in the first figure, whereas the trajectory is an iso curve in the surface of both other figure. In both examples, all section instances were scaled with the constant vector. So this constant vector plays a crucial role. Swept surface problems. The most challenging problem in this field has been the identification and visualization of the boundary, especially for those volumes that are based on free-form geometric entities. In the two figures displayed there, the first figure is trajectory is not interpolated, and in the second figure trajectory is interpolated. One of the swept surface problem is self-intersection and the other one is wavy surfaces. In self-intersection, to unambiguously represent a solid volume, it is necessary to identify and trim away extraneous and distracting paths caused by self-intersecting regions of the boundary surface. Another problem that swept surface causes is even incorrect curve placement causes flipped surfaces. In the second figure, we can clearly see that when we place an incorrect curve, it causes flipped surfaces. Here the section curve is placed by the Freinet frame. Better curve placement with a local moving frame. In the first example, trajectory is planar, whereas in the second one it is twisted. In both cases, the moving B of BV is drawn with a solid arrow and the Freinet frame axes are plotted dashed. Coming to Gordon surfaces, it is a spline blended surface. Interpolating the network of curves is known as a Gordon surface. We can clearly see the Gordon surfaces represented with some control points. We are given a network of curves as mentioned above. It is decided to construct a surface G U of V interpolating the given curves. Let us denote given U curves and V curves. So, the U curves can be denoted from 1 to n and the V curves can be denoted from 1 to m. These curves intersect in points as shown in the equation. Hence, the Gordon surface is defined by G1 plus G2 minus G12. And Li power m of u are blending functions satisfying Li power m of u of I equal to 1, Li power m uk equal to 0 where I not equal to k. And the equations for G1, G2, G12 are given here. We'll use B2 splines to construct appropriate blending functions. So the most interesting thing about the Gordon surface is adding two surfaces and deleting a third surface. Gordon surface construction. It is U-directional lofting. These are the examples for Gordon surface construction using U-directional lofting. In the first figure we use control net, whereas in the second we use surface interpolating V curves. Another method is V-directional lofting. In the figures shown here, the first one uses control net and the second one uses surface interpolating U curves. Another one is tensor product surface. Similarly, in the figures shown here, in the tensor product surface, we use control net for the construction of a Gordon surface in the first figure, and the surface interpolating intersection points can be clearly seen in the second figure. Construction of Gordon surface from three surfaces. Control net, surface interpolating U and V directional curves. In the first figure, we use control net for the construction of Gordon surface from three surfaces. for which we'll get the final equation as P51 equal to P51 power L1 plus P51 L2 minus P51 power T. And in the second figure, we can easily see the surface interpolating U and V directional curves.
Hello everyone, let's see what Coons surface is. Coons surface is a type of manifold parameterization used in computer graphics like CAD to smoothly join other surfaces together and to mesh problem domains into elements in computationally mechanic applications, and more particularly in finite element method and boundary element method. It means that manifold means various. So you have a type of various parameterization in cone surface, and that is more particularly in computational mechanic applications, in finite element method and boundary element method. A family of parametric surfaces called Coons patches was developed by Steve Coons, and it is named after his name. They are defined by boundary curves around the parameter of the patch and blending functions that are used to interpolate a surface between the boundary curves. So the cone surfaces have the boundary curves and a blending function to interpolate the surfaces between the boundary curves. Cone patches are a subset of tensor product surfaces. So next, we have the cone surface construction. So here, the classical cone surface is generated by having four boundary curves. But in a generalized cone surface, we have four patches as the input instead of the four curves. The four patches are defined on the same parameter domain, and one boundary curve of each forms a side of a curvilinear rectangle. So the four patches that we have for the generalized cone surface are defined on the same parameter domain. The resulting surface interpolates these boundary curves, and its shape is influenced also by the shape of the constraint parts. So when we get the resulting surface with the boundary curves, there are different constraint parts that make up the surface, and if the constraint parts a little bit influence, the shape would also change. Next, the construction presented ensures only a continuous connection of the generated surface to the constraint parts along the common boundary curves. So here we can see three different cone surfaces. The generalized cone surface is defined by four rectangular surface patches, as we have seen earlier. So by changing the shape of the constraints, the shape of the resulting surface will change as well, even if the boundary lines are fixed. This case can be illustrated by changing the bump on the patch in the front. So here we can see, even if the boundary lines are fixed, the resulting surface will change if there is a change in the shape of the constraints. So here you can see the illustration by changing the bump on the patch in the front. So you can see a bump in the front. So that change is a resultant of the change of the shape of the constraints. Next, bilinear Coons patch. So the bilinear Coons patch is a class of Coons patch obtained when there are four boundary curves and the blending functions are linear. As we have we have seen in Coons patch that we have four boundary curves and a blending function. So in bilinear, we have these four boundary curves and the blending functions are linear. So here, as seen in the diagram, we can see, suppose that we want to create a surface PUV over the unit square that interpolates the four boundary curves PU0, U, PUIU, POVV, and PIVV, which correspond to the bottom, top, left, and right of the square as shown in the figure. That is, we want PUO is equal to PUO, PU1U is equal to PU1, and so on for all U and V. For surface modeling applications, P will typically be a 3-vector. This is an important thing. So in the generalized surface modeling applications, we require P to be a 3-vector. That's PUV is equal to PXUV, PYUV, PZUV. So it's PX, PY, PZ are the 3-vector. But the Coons patch can be generalized to arbitrary dimensions. So next, let's see what are parametric bicubic surfaces. So we have different types of parametric bicubic surfaces. Those are Hermite surfaces, Bezier surfaces, B-spline surfaces. So the parametric bicubic surfaces generalized version is we have Qt is equal to T into M into G from parametric curves. To have a parameter in the other direction, we replace T with S. So Q of S is equal to S into M into G. The parametric bicubic surface is given by QST is equal to S into M into G into M into T. So we can see the G as the given matrix of G1, G11, G21, all the control points. So next, let's see the representation of cone surface. Here, the three vectors x, y, z are represented by xst is equal to s into mh into ghx into mht into t bar t. Y into st is equal to s into mh into ghy into mht into t bar t. Zst is equal to s into mh into gh into mht into t bar t. So this is an example of a bicubic surface. Here in the ruled surface, the four interpolantes QOT, Q1T, QSO, QS1 are all straight lines as we have seen in the figure below. Next, here the GH, as we have seen before, the matrix is the actual matrix is here. The upper left 2 by 2 matrix that you can see x00, x01, x11, x11 are the x coordinates of the four corners, and the upper right and the lower left 2 by 2 matrix gives coordinates for the tangent vector along each parametric direction. So we have different tangent vectors. So these gives you the coordinates of the tangent vector along each parametric direction. The lower right 2 by 2 matrix is the partial derivatives with respect to both S and T, and it's called twist. Next, Hermite permits C1 and G1 continuity from one curve segment to the next. So here Hermite permits the C1 and G1 continuity. So there are the different conditions for C1 and G1 continuity. Conditions for C1 continuity are that the control points along the edge, the tangent vector and twist vectors to be equal. For G1, the vectors must have the same direction, not the same magnitude. Next, let's see what is Bezier surface. Bezier surface is derived the same way as the Hermite. Here, xst is equal to s into mg into gbx into mbt into t bar t, and y is same as follows, z is same as follows. The geometry matrix G consists of 16 control points in Bezier surface. Bezier surfaces are attractive in interactive design. The surface interpolates some control points, convex hull subdivision. That is why it is more interactive in design. Next, C0 and G0 is created by making the four common control points equal. So this is the representation, and G1 occurs when two sets of four control points on either side of the edge are collinear with the points at the edge. A Bezier surface is represented using this equation. Xst is equal to 1 minus t whole cube, 3 into 1 minus t whole square, 3t squared into 1 minus t into t cube into gbs, and the given matrix 1 minus s whole cube, 3s into 1 minus s squared, 3s squared, 1 minus s cube. So this is the representation, and it has the diagram, and it has a common edge here. So this is a Bezier surface example as shown in the figure. Next, B-spline surface. The B-spline surface are represented as xst is equal to SMBS into GBSX into MBST into T bar T. Y vector is given by S into MBS into GBS, MBST, T into T, Z is S into MBST, GBS into MBST into T bar T. So these are the different three vectors. B-spline surface come naturally with C2 continuity. In Hermite, we have seen it has C1 and G1 continuity. Here, B-spline curves has C2 continuity. All techniques for subdivision and display carry over to the bicubic case. So next, let's see what the design examples are. So this is the design example for the swung surface, and these are the different control points and the curve that is formed due to the control points. And this is the example for skin surface. Here you can see that you have different curves aligned, and their direction gives you a certain surface. If you change the direction, you get another surface. And here also you can see a skin surface. So you have four different curves, and their alignment in a particular direction gives you this surface that we got at, which is there at the bottom of the slide. Next, this is an example of surface. We can see it has different control points and the curves. This is the example for Gordon surface. This is the example of Coons surface. Here we can see that it has four curves. As we can see, have the four boundary curves that we have learned in Coons surface. And the next part of the diagram shows you that it has four control nets and four Coons patches. So these are like for the garden and for the cones. And now this is the one we have tried out. So this was our idea to form coffee cup. So we thought we could have three curves. In this was our basic idea of how to do to have the curves aligned in vertically. So next, using Blender, we first made this with the different control points and with different sectional curves, and then we gave a slight lightening and smoothing to it so that we could get a smooth surface and a skinned surface as seen in the figure. Next, we have given a color to it and a handle to it and formed it to a coffee cup. And this is a final thing with a proper color, with the proper design, and the final skinned surface with proper smoothing. We found the final coffee cup surface that we found using Blender. Thank you.